Evolution is arguably one of the strongest processes in our natural world. So today in this Unity video, I will show you how I simulated it. So we begin with 10 agents. These agents are just basically simple blocks with a nav mesh agent and a speed. The speed is the important part. The speeds are set randomly, sort of like genetic variation. So if we scroll down, we can actually see like this guy seems to be pretty fast. So he got lucky and he has a speed of 6. So we're gonna name this guy Alpha, and the Alpha bloodline. Now you can see that Alpha actually is no longer the only Alpha. There is actually a second Alpha, which is basically his child. So he has a clone, and this clone speed is set by the parent speed, but there's some added genetic variation. So this clone speed, actually, Alpha got lucky. So Alpha speed is 6, and his child speed is 7. This isn't necessarily the case. His child speed could have been like 5, or even like 3. The speed is determined by a normal curve. So some clones will be faster, and some clones will be slower. You can see this clone actually appears to be much slower. If I pause it, this is a 1.7, so it's a lot slower than sort of the others. Now, when they reach the end, if they're in the top 10%, then they actually are able to clone themselves, and their clone stats are based on their stats. So we essentially have sort of little bloodlines. So actually this is set so the bottom 50%, actually, if I check my evolution manager, the bottom 50% is killed and the top 50% gets to reproduce. So this is a very high rate of turnover. You can also see, so there's 10 agents total. Just got our simple agent. The agents all have a nav mesh agent pointing towards here, and the top 50% get to reproduce, and the bottom 50% are killed. So we also see that the lighter, the more times it's been cloned, the lighter it gets. So you can see this clone actually, which has a speed of 11. You can see they're evolving very fast. This has a pretty light shade. So, and you can see it also just created a new clone. Let's see how fast its clone is. Its clone looks like it's really fast. Its clone looks like it's a 17, which is actually incredibly fast. So this Alpha bloodline is rapidly dominating the other agents' bloodline. Seems to be going extinct. I guess maybe not. This one will survive. But if we take a look at the bloodline so far, we see that there are 1, 2, 3, 4, 5, 6, 7, 8 alphas, and there are only 2 agents then. Yeah. So, and that might even change. There might not even be any agents left. Yep, okay, the agent bloodline has gone extinct. It is now, everyone is alpha. So I'm probably one of the fastest. So, yeah, he's got a speed of 17. Let's see, and we seem to have some agents that are even faster than this. So if I pause it, I click on this. This guy is a speed of 20, and this guy is a speed of 21. So you can see the agents are very rapidly evolving to get increasingly fast. Now the interesting thing with evolution is that eventually these agents will start. Yeah, you can see these 5 guys are all going to be killed, and these ones duplicate. So the interesting thing is that you can select from multiple environments. You don't even need to know what you're selecting for. The environment does it for you. So you can have like 1,000 variables, and over time it'll take a lot longer, of course, but this system should be able to select for anything. So it's a very generalizable system. One of the things I'm interested in is neural networks, and neural networks have the problem of not being very generalizable. So what I'm interested in is using gradient descent and evolution to create something that's slightly more generalizable, something that has more potential for change, sort of like how humans exist. So you'll eventually start to see some of these clones are going to get really, really fast. And eventually their speeds will actually stop mattering. The genetic selection will stop around, I believe, about 100. And the reason for this is because the only thing they have control over is the speed. I haven't given them the ability to evolve acceleration. So I do have another scene where I can do that. And so it's interesting to see what evolution selects for. You can see these seem to be getting consistently faster. But at some point they're going to level off around 100 or so, because they can only accelerate at 8 meters per second. So with that barrier, eventually they're just constantly accelerating, and there's no chance, and then it all becomes luck on how they spawn. So you can see where they spawn here. Some are near the front, and some are near the back, and the ones near the back don't have much chance. But you can see there's definitely some of them are definitely still faster. So there's still a little bit of evolution happening, getting up to 116, 73, 107, 137. (104), 137, 66. So there's definitely some selection pressure, but the selection pressure is now pretty lessened. What will be interesting is to run this simulation experiment on something else. So now you can see they've pretty much evolved to a rough, like, finishing point. There's not too much more they can evolve from here because they just don't have enough time to accelerate. We'll still get some very high numbers, by the way. Like, we're gonna have like top speed is like 1,000 or something. But in general, these are already fast enough to do everything they need to do. So yeah, let's end this and take a look at the code. So the way I wrote the script is that I gave these agents, first I sort of have like an agent total variable. I've got agent spawner, and then basically the model for the starting agent. I've also got a value for increasing the shades. You can see which ones are clones. You can see all those were turned basically white, and that was because their shade kept increasing. I have just a couple of variables, including delete the weak, which removes, basically it checks to see if all the successful clones have finished, and then it just deletes the rest without even waiting for them to finish. Because if I did try to wait for these to finish, it would take a very long time sometimes. Like sometimes you get like agents that are like 0.1 speed. They just slowly crawl towards the destination. But fortunately, since it's distributed along a normal curve, you get a pretty nice distribution. So you don't have to wait too long generally, depending on what you set your number to. One interesting point is this random Gaussian function, which is what I'm using for Gaussian. I've never actually quite gotten that. This sets the clones variables along a normal curve, and so like the typical normal curve is like it's basically just like the bell curve. Most values will fall along the center, and then a few will fall along the edges. This one is actually capped at 3 standard deviations. So the most you can get is 3 standard deviations. So the very highest value you can get is like 7, and the lowest value you can get is like 0, because we set the genetic variance right here. So this is one spot. This is where we start setting genetic variance. We take their speed, and then we basically add it to its speed times a random Gaussian. So if it gets -1, then its speed will actually just be 0. If it gets +1, then its speed will be 7. So we can basically see how this sort of continuation, like this structure, allows for evolution in a certain direction based on this random Gaussian. Now there is some argument to be said that like maybe we should have something like the random Gaussian itself should also evolve. Like maybe you want to take big steps at the beginning, but little steps afterwards, and you wanna find some sort of niche. This is where evolution is not as optimal. So that's something I'm going to be experimenting with in the future. Lastly, this is just the code for adding the agents to basically this is the code for keeping track of the agents and then destroying them or adding them to a second sort of set, basically agent 2, and the agents in agent 2 are basically just waiting, and then they're set back to agent 1, and the previous ones are destroyed. So that's sort of how I'm handling that. I'm going to make this all available on GitHub, and I'll show you a quick sneak peek of what I'm doing with sort of some of the more advanced and more complex evolution. So for this one, we have a path. So this might mean that top speed is not necessarily the best. I also have 100 agents for this, and these agents have multiple values. So not only do they have top speed values, they also have acceleration. So you can see this guy's acceleration is a little bit higher than normal. His angular speed is also a little bit higher. And interestingly, if you check out my evolution manager, I have it so the standard deviation is actually less. So it's more likely, a random evolution is more likely to be bad. It's more likely to decrease the speed, and I'm testing this to see if this structure will ultimately result in evolution that devolves, or if it still manages to converge to an optimal solution. So the top 10% get to basically reproduce, and the bottom 10% are killed. And so this sort of slow method will eliminate. You can see these 10, like, yeah, these guys are all gonna die. They're too slow. So of course there's lots of ways of making this more efficient, like especially not having this be quite as long. But at present it works pretty well for basically just it's very generalizable. Like I can set this to anything. So on a shorter map, acceleration might matter more. On a longer map, top speed would matter more. And so I want to train them in the environment that they'll ultimately be working on. So that's the evolutionary progress so far, and I'll update you with more details.